introduce briefly you. Hello everyone and welcome to this session of the FGC IPM number theory webinar series. Today our speaker is Dr. Reza Taleb. He received his Bachelor and the Master of Science degrees from Sharif University and got his PhD under supervision of Professor Manfred Cluster from McMaster University in 2012. And currently he is an assistant professor in the Department of Mathematics in the Shahid University. His research interest consists of many various subjects in algebraic number theory, such as Iwasawa theory, p-adic theory, and algebraic Lie groups. The title of his talk is the Coates-Sinnott Conjecture. And Dr. Reza, you may start your talk whenever you want. The time is yours. Thanks, everyone. And you can share your screen and start as you want. Thanks a lot.
Okay, thank you very much for your invitation. I have to thank the organizers in the beginning, and I try to explain this conjecture by fixing my notations. First, I let E to be a number field. And I let F to be another field inside E, and I assume that the Galba group is denoted by G is abelian. Then I let S to be a finite set of primes in the base field in F containing ramified primes I mean all ramified primes in the base field in the top field and infinite primes. For simplicity, we can just take this finite set of prime to be exactly the set of ramified primes of F inside E and the infinite primes. And I let the equivariant L function, I mean Artin function to be defined as this sum theta E over F. This is my notation at little s, and this one is a capital S, to be defined as this sum, the summation over all characters inside G, I mean all characters of the group G, the Galba group of E over F, and the L function, Artin function, I mean S incomplete Artin function of this extension corresponding to this character and the value S times the eigenspace E chi, where I introduce these notations by Artin function of this character and the value, I mean exactly the product over all primes in the base field, not inside the set S. And since S contains all ramified primes, So all primes in this product would be unramified. So the Frobenius elements for these primes are well defined. 1 over 1 minus, as we know, the character acting on the Frobenius of this prime over norm of prime to the power of s. So this is the Artin L function corresponding to this character and value s. This is capital. And E chi is just eigen value that I define to be 1 over the cardinality of G and this summation chi of sigma inverse for running over all elements of this Gauss and inside G. So I get an element in this group ring whose coefficients are all complex. This is the setup of my notations, and in the next step we can say that so this one is just RT S incomplete. I mean the Euler factors corresponding to the primes inside S are all removed. Then I have to say that by the result of Ziegel 1960, we know that if we evaluate these equivariant ordinal functions at spatial values 1 minus n for any integer n greater than or equal to 1, we get an element of the this group ring whose coefficients are all rational. So in spatial values, I mean for any integer n greater than or equal to 1. And this element would be, all coefficients of that element would be rational. In the next step, I have to recall the result of Kessler. Notice and independently the lean and rivets around 1980, saying that if we multiply this element in this group ring by suitable coefficients, I mean the cardinality of this group H0 of F and Q over Z n. I mean, for this notation, I mean the Tate twist. I'll explain this notation a little bit later, but this would be easily computable. If you multiply this number by equivariant main L function at spatial values 1 minus n, then we get all coefficients be integral. for any integer n greater than or equal to 1. And for simplicity, let me just call this element to be the Stickelberger element of this extension. And I consider the primes inside S, which are removed through Euler factors in the definition of the L function. So this would be evaluated at 1 minus n. So this is the notation that I will use in the rest of the talk. Now, the result of the classical theorem of before stating the classical theorem of Stickelberger, let me remark that by functional equation of L series, L function, the Stickelberger element would be 0, 1 minus n, unless f is totally real and chi of minus 1 is equal to minus 1 to the power of n. So if f is totally real and the character is even, n should be even number, and if the character is odd, n would be an odd number. In these two cases, the Stickelberger element would be non-zero. Other than that, we get a zero element of the Stickelberger. So we have two interesting situations. The first is that f is totally real, field, and E is totally real, and N is just an even number. And the second situation would be E over F is a CM extension. Top field is just CM field, and the bottom field is totally real field, and N is just odd. So we get two non-trivial statements in these two cases. Now, the Stickelberger theorem says that Stickelberger's theorem 18 says that we can just take Stickelberger of S at 0. Here I let n to be equal to 1, and I let f to be q. For the extension E over q, and as an element of the integral group ring ZG, this would be in annihilator ideal over the integral group ring of G of the class group of E. So this is the classical Stilberger's theorem. So letting just n equal to 1 and f equal to q, I get the classical Stilberger's theorem. Now we can generalize this Stilberger's theorem in two different directions. The first, generalizing in two different directions. The first one is the celebrated conjecture of Boomer. Conjecture, saying that we let n equal to 1 and f to be arbitrary number field. Arbitrary number field. Then this conjecture predicts that the Stilberger element of this extension at 0 would be an annihilator ideal of the class group of E over the group ring ZG. This is one direction, and there are some results. However, this conjecture is mostly open. And the other direction is the Coates-Sinnott conjecture. Coates-Sinnott conjecture 44 74. And in this direction, we let n to be an integer greater than or equal to 2, and we let f to arbitrary number fields, arbitrary totally real number field. So in the rest of the talk, I want to explain the second direction, the Coates-Sinnott conjecture. So if I want to formulate this conjecture in terms of algebraic K-groups, I get this terminology, conjecture.
Excuse me, can I ask you a question?
Sure.
So why are these two different directions? I don't understand.
I mean, in this, in the first direction, I just let n to be just equal to 1, and I think about the annihilator ideal of the class group. And in the second direction, we just let n to be arbitrary, integer greater than or equal to 2, and f again arbitrary. And we think about the annihilator ideal of the K groups instead of the class group that I will.
So you can write the.
Sure, I will write.
So what is the
code?
I'm sorry. What is the Coates-Sinnott conjecture? What is the Coates-Sinnott? You didn't say it yet, right?
Yes, I didn't. So I'll explain this slide. Coates-Sinnott conjecture. The K-theoretic version. In this conjecture, we have Stilberger ideal of the extension as incomplete ordinal functions equivalent to incomplete ordinal L functions multiplied by a suitable factor evaluated at 1 minus n would be an annihilator ideal over the integral group ring ZG of K2 n minus 2 of the integral ring of E. I mean the ring of integers of the top field. This is what Coates-Sinnott conjecture says for any integer number greater than or equal to 2. So this is the first formulation of this conjecture. So we take n arbitrary integer greater than or equal to 2, and then we evaluate Stickelberger ideal at 1 minus n. Then this conjecture predicts that this element would be in annihilator ideal of the k groups of order 2 n minus 2 of the ring of integers of the top field, I mean E. But I have to say that's up to 2 torsion. So we have to get rid of the 2 parts of the both side, and then we can say this formulation. In the next version of this conjecture, I have to take the ethyl cohomology groups, and from that point of view, these 2 torsion parts would be more clear. Okay. Sule constructed the Chern classes, Chern characters from constructed Chern classes. And he defined the map from k to n minus 2 for E, tensoring by Zp, the p-adic integers, going to the ethyl cohomology groups, the second ethyl cohomology groups of these guys. I will explain what this means. Zp, and using Chern characters. Here, by this notation, I mean ethyl cohomology groups. By this notation, OE prime, I mean spec of OE, and P is inverted in this area, and I can the coefficients to be in P and in the mu Pm, all roots of unity of order P to the M, tensoring n times by itself, and then we take the inverse limit of this object over M. This is what I mean by the right hand side notation. And it was proven that this map is just an isomorphism of groups for any isomorphism for any odd primes. Isomorphism for any odd prime P. So this is exactly the link of the algebraic K groups to ethyl cohomology groups, which describe the Coates-Sinnott conjectures in terms of the ethyl cohomology groups. And for the prime 2, the situation is a little bit different. For P equal to 2, we have 3 different cases. In the first case, If 2n minus 2 is congruent to 0, 1, 2, or 4 mod 8, again we get isomorphism. If 2n minus 2 mod 8 is equal to 3, we get surjective map with kernel equal to z over 2 to the power of r1, and here by r1 I mean the number of real places of the top of the bottom field, I mean f. And if 2n minus 2 mod 8 is congruent to 6, this map would be injective with co-kernel equal to isomorphic to z2 to the power of r1, and here r1 is r1 is the number of real places, real places.
Sorry, there is a question.
Sure.
How can 2n minus 2 be congruent to an odd number modulo 8?
We don't have this situation here. In general, we can just put instead of 2i, and we can change I between 1 and 2, and then here I can just put I. So in this situation, I equal to 2. We don't have these situations. Thank you. Thank you. So I can omit and these situations. Okay, so and this is a result of roughness. This unviable, and we can describe the conjecture in terms of equal cohomology groups. Before that, it's good to say that the K groups of even orders are all finite groups. I will explain this. So maybe it's better I explain this before. And these are all finite groups. All K groups of even order are all finite, and we can just say that K, I mean for any n greater than or equal to 2. When n is equal to 1, we get K0 of OE, which is isomorphic to the class group plus Z. So the torsion part of K0 is just the class group, and so we can think of the K groups of even orders as generalization of the class group. So we can explain the Coates-Sinnott conjecture, conjecture in terms of Italco-homology groups. Homology groups version. And here we can say that the Stickelberger element the Stickelberger elements of this extensions at 1 minus n are all in annihilator ideal of the second Ital cohomology groups by the notations I O E prime and the coefficients in ZPN, which was described before. And we take this annihilator ideal over the group ring ZP. So we localize the conjectures for any prime, for all primes P. If I want to be faithful to the K-theoretic versions, I let P not equal to 2. However, we get some results for P equal to 2 that I will explain later. So, and this is for any n greater than or equal to 2. And this is the second version of the conjecture, which is equivalent to the previous one. In the next step, we can just take the motivic cohomology groups, the second one of the field F, and the coefficients Zn, and tensoring Zp. This is what Pushing did, and going to Ital cohomology group. And ZPN. All right. And for any prime, for any P prime, including P equal to 2. And it would be isomorphism. And these isomorphisms, I mean, the previous one and this one, is just the Lichtenbaum, Eulen-Lichtenbaum conjecture. Conjecture, which is concluded from Bloch the conjecture that is proven by Vygotsky, and so we know that this conjecture would be true. So we have all these isomorphisms that I said. So we can say the third formulation of the conjecture, the Coates-Sinnott conjecture. In the motivic version. Version of the conjecture, which says that the Stickelberger ideal of 1 minus n would be an annihilator ideal of the motivic cohomology group. And so Stickelberger of this extension corresponding to the set of primes that contains all ramified primes and infinite primes. 1 minus n would be an annihilator ideal of monotypic cohomology group. The second one, I mean here, sorry, E. E coefficients in Zn. And this is again a global version. So we get another global version of this conjecture. And here, if we want to be faithful to the original conjecture, we can say that up to 2 torsion. And from the isomorphisms above, we get that the monotypic version is stronger if we get rid of this statement. I mean, up to 2 torsion. If we omit this statement, the monotypic version would be stronger. And if we let the ethyl cohomology version, and if we conclude p equal to 2, then the monotypic version and the ethyl cohomological version would be equivalent, and these versions implies the k-theoretic version. So this is what the Coates-Sinnott conjecture says. So for this part, if you have any question, please let me know. Before stating the results for this conjecture, let me make another comment. Mark. We can say that for some situations, we can say stronger formulation for this conjecture by replacing annihilator ideal by fitting ideal. So more strongly, one can conjecture that the Stiglberger element of this extension corresponding to the set of prime S at 1 minus n would be inside the fitting ideal. We can say all these versions, for instance, K2, n minus 2. And fitting ideal, as you know, is a submodule, the subring of annihilator ideal, which is constructed via the certain minors, and the annihilator ideal to the power of q, if q denotes the number of generators of the ring, would be inside the fitting ideal. So fitting ideal is inside the annihilator ideal, is some part of the annihilator ideal, and annihilator ideal to the certain power would be inside the fitting ideal. So this statement would be strong. And I have to point out that in many cases we have equality here, and we can say that the ideal generated by this Stiglberger element would be exactly equal to the fitting ideal of this K groups of even orders. So this is just a remark, and so if you let, I'll go to the results. Corresponding results. For F equal to Q, I let the base field to be Q and N to be even. So I let the top field, I mean E, to be totally real. The Coates-Sinnott conjecture was proven by Coates and Sinnott in the original paper. Coates-Sinnott, 1974. Another result is due to Burns-Greuter if is totally real. P is odd. So I want to take the second formulation. I mean the Italco-homological version. And P is odd and N is even. Okay, N is even, which are the interesting situations by the functional equation of orthogonal functions. And under some other hypotheses, and the main part of this hypothesis is just equality of mu is equal to 0. I will explain this condition a little bit later. And Burns and Greuter 2003, Kwang-Du using the equivariant main conjecture of a theory formulated by Ritter and Weiss. Equivariant main conjecture in theory. Kwang-Du did this situation under this strong condition u is equal to 0, and for all primes p which are odd. And Ritter and Weiss have a series of papers starting from 2001 to 2012 proving the equivariant main conjecture of a theory in general. Kwang-Du just used the abelian versions of this conjecture. I will explain what I mean. Another result is by Pesco and Greuter and Pesco. Here we can just take f to be totally real. Sorry, here if n is even, the non-trivial case would be E is totally real. This is equivalent. If I let E to be Cn field, and P to be odd, and N to be even, to be odd, and I let mu is equal to 0, then this situation was solved by Greuter and Pesco. In 2012 or 13 by proving another main conjecture in equivariant main conjecture in Iwasawa theory. This is what Greuter and Pesco did. For the case E to be totally real, and P is arbitrary. I let P equal to 2, and N is even, even under the assumption mu is equal to 0. I did the proof 2012. For proving this conjecture, I needed an equivariant main conjecture for all primes. I formulated a conjecture for all primes, including p is equal to 2, general formulation, and using that formulation, I get this situation and another. Let me just say p is totally real and p is odd and n is even, and we are in a semi-simple situation. Semi-simple. So by mean I mean p does not divide the cardinality of the Galba group. Then this is the work of Popescu, and independently around 2009. And another situation would be E to be Cm, complex multiplication. P is arbitrary, not necessarily prime, not necessarily odd, and n is odd. We get non-trivial Stickelberger element, and we are still in a semi-simple situation. So here, I mean, P does not divide cardinality G over 2. So it's a Cm field, so it is the degree would be even if I divided the cardinality of the Galba group by 2. P does not divide this cardinality, and this is a result of Coates-Sinnott and me in 2000. And I just saw a very recent result of nickel. It is not published, but he omitted the situation, and mu is equal to 0 in this case. In this case, just omitted this. Unpublished work of nickel. I want to find the name of the co-author. I wrote somewhere. He proved the equivalent main conjecture of the Reza theory in abelian case without assuming p is equal to 0, and as a result, you get this result. And he says that he used a recent result of Dasgupta and Kakte in 2021, who proved the Brumer-Stark conjecture in under some situations. And Nickel and his co-author used this unpublished work of Dasgupta and Kakte to prove this in another situation. And these are the relevant results. And if I have time, let me explain the sketch of proof, a very, very, very brief of sketch of proof by saying a couple of words. I mean, the general methods to attack to this conjecture would be through main conjecture equals of a theory. So sketch of proof and brief. If there's any question so far, please let me know. Okay, I'll say a couple of words about um, the way of attacking this conjecture through Iwasawa theory. We have to take F to be base field, E to be top field. This is just abelian extensions. I let G to be Galva group as I did in the beginning of the talk. And then we take E infinity. And E infinity is just, and here, let me just assume that this is totally real. For the CM case, we have to do some other results. If E is a totally real field, then under assuming the Leopold conjecture, we have just one extension over E, noting by E infinity, whose Galva group is just gamma, which is isomorphic to ZP. I write gamma as a multiplicative group and ZP as a additive group. For some reasons, we just use the multiplicative notations. If we assume the Leopold conjecture, then there is just one ZP extension of E, then E is totally real. In general, the number of ZP extension of a number field is 1 plus R2, when R2 is a number of complex embeddings. In the next step, we get a very big extension of E infinity. I denoted this by M infinity S. And this notation, by these notations, I mean the maximal abelian. This is why abelian main conjecture Iwasawa theory works. Abelian P, pro P extension, which are S ramified. By S ramified, I mean ramified of E. Just remember that S is a finite set of primes of E, which contains ramified primes and infinite primes. So I take the maximal abelian pro P S ramified extension of E infinity, and by S ramified, I mean this extension is unramified outside the primes of S. So for any primes outside S, we have ramification in this extension, and by these words, we get the maximal extension. And we denote this Galva group by this notation. So I let X infinity S to be exactly the Galva group of F and infinity S over A infinity. It's not really hard to see that since this is pro P, so it is just a ZP module And we can see that this Galois group, which is gamma times G, acts on this group. So gamma times G acts on this group. It's not really hard to see how. There's an exact sequence. There's a map from X infinity S to this Galois group F infinity S over the base field F, and the kernel would be sorry, uh, yes, and the co-kernel of this map would be gamma times G. And from that exact sequence, we can get easily the action of this group or on this module. So this implies that X infinity S is just ZP gamma times G module. And here we can just use a very simple isomorphism saying that this is just ZP gamma G module, and we denote this by lambda, which is Iwasawa algebra, an example of Iwasawa algebra. In the semi-simple situations, we have to take different characters of G and work on each character separately. But in the equivariant versions, we have to work with this whole X infinity S without going to any character part by part. And now here is what we are doing in these proofs. X infinity S, so is it just lambda module, lambda G module. This Iwasawa module is related through main conjecture of Iwasawa theory, to p-adic L functions, p-adic L function, which interpolates at spatial values. There's the interpolation at 1 minus n with the usual function. I mean, equivariant Artin L function. Equivariant L function. And in the other side, X infinity S as a lambda G module. We have to do some work in this part using some spectral sequences, using some facts and some theorems in Iwasawa theory, and doing some works by taking some other technical stuffs like Tate twists. There are some decorations like Tate twist, descent, by taking some co-invariant of this module under this Galois group gamma, and some other stuffs like Contrarian dual. We relate this algebraic part of Iwasawa theory to Italco homology part. I mean the second Italco homology groups of OES ZPN. So if you have a suitable main conjecture of Iwasawa theory, equivariant version or the original version proved by Wise, then we get this connection here. So we can relate the Ital cohomology group to equivariant L functions. And finally, just let me say that what mu is equal to 0 means. If we say that mu is equal to 0, it is some part of the main conjecture and something like that, which we know that this is proved for a billion extensions. I mean, if F over Q is a billion field, then Ferrero and Washington showed that mu is equal to 0 in this case. What I mean by this is that mu is equal to 0 means x infinity s. For semi-simple situation, we have work character by character, but in the equivariant versions, we can say that mu is equal to 0 is equivalent to that. Mu infinity s is just finitely generated ZP module. So this is the way that we are thinking about this conjecture, and if we assume that mu is equal to 0, so for all primes, assuming mu is equal to 0, the result would be true, and there is some work of Nickel says that we can omit mu is equal to 0, but just for odd primes. Again, p is equal to 2 is completely neglected. Okay, thank you so much. This is what I wanted to say.
Thanks a lot for your excellent talk. Are there any questions?
Do you hear me?
Yes.
Yeah. I have a question about it was our theory in the general case that if we work over the field of rational numbers, the cyclotomic fields or the Ray class fields, especially the p to the n power cyclotomic fields, are Ray class field, narrow Ray class fields with prime power conductor. My question is that why instead of working with for a general number field, for a general base number field, why instead of working with narrow Ray class fields with prime power conductor, just work with against atomic towers?
Right. Actually, here ramification is completely restricted. You know, if you take ZP extensions, then we know that all primes are unramified except the primes above the prime P. So any gamma extension, or I mean ZP extension, would be P ramified. I mean, other than the primes above P, any primes are unramified. And this is what we need in main conjecture of Iwasawa theory.
Yeah. Okay. I said maybe we can work with narrow Ray class fields with prime power conductor.
With prime power conductor.
Yeah.
I'm not really
Even
sure
ideal
that
in
field
base
would be
field case.
exactly the same or not. But right. Here, their ramification is allowed, and I'm not really sure what you are saying is exactly the same as the ZP extension or not. I have to think a little bit.
Yeah. The problem is that the may be not a ZP extension, and but the ramification is only
Yes,
appear for just one prime. But
exactly.
yeah,
Exactly.
is there
Right. It
any
is not
control?
exactly correct.
Yes. Uh, is there any control
We
on
don't
the
have any control
on
on
this?
the game.
I'm sorry. I mean, is there any control on the Galois group of this tower working narrow glass field with prime power conductor?
Hmm. I'm not really sure. Maybe in class field theory we can say a couple of words about that. But what I know that we can replace ZP by any compact Lie groups, and we get another versions of main conjecture in Avogadro theory. And this is just one-dimensional case. I mean, um, for instance, in the original version of the main conjecture that was proved, we take a character which is one-dimensional, and we go through this character. But if we take some representation of higher dimensions, then we can replace ZP by any p-adic Lie group, which is compact, and it needs a couple of technical conditions. Then we can formulate the main conjectures for that situation. But for narrow class field, I'm not really sure if we have some uh, control on this. I'm not even sure that it is just a p-adic Lie group or not, and this is compact or not. These are what we really need in the main conjectures: p-adic, Lie group, and compactness.
Thank you.
You're welcome.
Okay. Any question else?
A non-trivial Stickelberger element only when f is totally real and n is even if e is totally real, or n is odd and e is cm.
Oh, thanks. And what is the reason? I mean,
Sorry, cm. I made a mistake. I mean totally complex.
totally
So
complex.
e
And
is
what is
totally
the
complex.
reason for these exceptions case? I mean, what is the totally real for L uh, help for the results? Why?
Right. If you look at the functional equation of a function, in the both sides you can see gamma functions. You can see R1, R2, where R1 is a number of the real places, and R2 is number of complex places, and we can just work out over um, the poles of the gamma functions and comparing the order of poles, and through that we get that if R1 is not if R2 is equal to 0, then we get a non-trivial statement, and
Oh,
n,
great.
as I said, would be.
I see. Great. Thanks. Thanks for the complete answer.
Yeah.
And any question else? If there is not questions, we may finish this session.
Thank you
And
so much for your inviting me. At the
okay,
beginning of talk, I saw a name of Boomer, and it was a little bit uh, fearful, but no, I don't see the name of Boomer in the participants.
Yes, you're right. He was here. I didn't see. I don't see it now. Okay, thanks. Let me know to say again thanks for your excellent talk.
You're welcome.
I mean, thanks for your acceptance to have talk in our seminars. And before ending this session, let me to mention that our next speaker is Shabnam Akhtari from Oregon University, and her talk will be held at 2 weeks later from now. So I hope see you all there again. Thanks for your attending, and thanks again for Dr. Taleb for his excellent talk. Okay, I should stop the recording.